Welcome, everyone, to the Ontologies Summit 2025. Theme this year is conceptualization, analysis, and formalization. The two sides of ontology, relating ontologies to the world, and two theories about the world. Today is February 12th, 2025, and we're very honored to have Barry Smith as our speaker. And the chair of our meeting today is Gary Burcross, and I will now give the floor over to Gary.
Thank you very much, Ken, and welcome all. And before we start, I wanted to just remind people as we passed track one presentations that our talks are very deep and rich, and we hope to have time for questions and answers depending on the availability of our speaker. And we'll see how that goes. And we'll also maybe have time to announce our next session so people who are attended here can know what's coming next week and as we move to track two. So with all that, it's a great honor to welcome Barry Smith back to the summit as a fourth track one speaker for this year's summit. Barry, like Nicola and Michael, is familiar to many of us here at the Ontology Summit as well as our forum. And like them, is justifiably called one of the founders of the modern field of ontology. I think at one point he changed his title from philosopher to ontologist. Like them, he also was a principal contributor to our first summit in 2006. And since then, he has been an organizer of summits such as the 2010 summit with the topic of creating the ontologists of the future. He's also been a frequent speaker at summits and has served on the IAOA advisory board. His early contributions to this field include Truth Makers from 1984, which was alluded to by Giancarlo last week. According to Google Scholar, his publications have been cited about 52,000 times. His 2007 article, The Obo Foundry Coordinated Evolution of Ontologies to Support Biomedical Data Integration, has over 3,000 citations itself. Barry's short bio, which is linked to on our site, provides some detail, and his site at Buffalo, which is ontology.buffalo.edu/Smith/, describes him as, quote, prominent contributor to both theoretical and applied research in ontology. He's a SUNY Distinguished Professor of Philosophy at the University of Buffalo, with joint appointments in the Department of Biomedical Informatics, Neurology, and Computer Science and Engineering. He's also director of the National Center for Ontological Research, as you see on our screen on his slides. As most know, Barry's pioneering work on the science of ontology led to the establishment of the basic formal ontology, BFO, which you'll hear about, I think, today in part, which is among the most commonly adopted top-level ontology development frameworks and was approved as an ISO standard top-level ontology. His work led also to the formulation of OBO, Open Biomedical Ontologies Foundry, a suite of interoperable ontology modules designed to support information-driven research in biology and biomedicine, which was one of the focuses of our 2023 Ontology Summit. And finally, I know that Barry's talk, with the modest title of, as you see here, Models, Theories, and Ontologies, and its broad scope intended to sketch out how the ontologies of classical and modern physics relate to the ontology of common sense and mathematics, will add an important perspective to our summit, this track, topics, as well as our discussions. So with that, please welcome Barry Smith to our 2025 Ontology Summit.
Thank you. So this is the official title, but what I'm going to be talking about has implications for views defended by someone who calls himself a techno-philosopher by the name of David Chalmers. He's probably in the top 3 or 4 living philosophers. And he believes strange things about physics, which we will be using as a foil in our discussion of ontology of physics, mathematics, and common sense reality. So as I think some of you know, I published with Jobst Landgräber a couple of years ago a book about AI, which is depicted here. Jobst is actually in the audience, and he will take part in the discussion, since what I'm going to be talking about has implications also for understanding the limits of AI, which is what the book is all about. And the Chalmers thesis that I will be addressing is put forward in this book called Reality Plus. And it will become clear the role that Chalmers' writings play in setting forth the ideas in this talk. So Chalmers thinks that before long, and assuming that there is no nuclear war or something to interrupt the matter, we will solve physics in something like the way that we solved chess, and thereby be in a position to create a perfect digital simulation of reality. He thinks that all of physics is based on quantum physics, which is in a way true. If we can solve quantum physics, we can create a perfect digital simulation, and people will happily allow themselves to be, I'm not sure what the correct word is, uploaded into the simulation, because it will be just the same reality as the one we're already living in. It will just be digital rather than real. And of course, it will be better because up there we will live forever. And so he says that he longs to come back down here on Earth every so often to take a look at how the Earth is, the real Earth is doing, while he enjoys himself immortally in his digital simulation. This is, of course, all nonsense. All right, now, our publisher requested that we create a second edition of the book, and this came just about 2 years after it was first published, because the book was something of a success. I think partly because nearly every university in the world is setting up many new courses and even whole faculties devoted to AI and, for instance, ethics or logic or ontology even. And so these courses are going to need textbooks. And this is a textbook dealing with AI and many other disciplines, including computer science and even AI ethics and anthropology and neuroscience and so forth. So it's a very cosmopolitan book. All right, now this book contains a new chapter on physics, which is designed basically to show why David Chalmers is wrong. And one of our major sources in that chapter is a book about particle metaphysics by a brilliant German physicist by the name of Falkenborg. And she is pessimistic about the possibility of even having a unified theory of quantum physics of the sort that people are working on. She thinks that particle metaphysics is going to be stymied from creating a unified theory, perhaps forever. And similar views are defended by the great English philosopher of science, Nancy Cartwright, who holds that, our idea that we can have a single unified set of laws of physics is wrong. And I'll be giving some of the reasons for that in the course of this talk. All right, the basis for the talk is the work that we set out here. It's very, very much a draft of what we hope will be ontologies of common sense, at least of classical physics and of mathematics. We won't be building these in their entirety. We will be showing how they can be built in the expectation that at least some portions will be built in great detail for specific use cases, for example, industrial use cases where physics or materials science ontologies are required. So this work is designed to provide a kind of foundation for some of those kinds of efforts. And to fit in with the theme of this particular part of the Ontology Summit, I'm going to talk a little bit about models. The word model will appear all the way through the talk. For the moment, it's important to recognize that models are created by human beings to describe, explain, or predict behavior. There are predictive models. And but not all models are predictive. We will be concerned with both kinds of models. And the AI book that Jobst and I wrote is based on the idea that there are systems for which we can build predictive models. For instance, the systems represented by engineered artifacts. But then there are many, many systems, perhaps nearly all systems, for which we can have no predictive models. And all organic systems are of that sort. We can have very few predictive models regarding the behavior of human beings. For instance, we could have a predictive model which says that sleep follows wakefulness, but that is a predictive model of the human behavior, but it's not anything that you can use, for instance, to engineer a digital clone of a human being. So it's predictive models which make engineering possible. All right, now our target models here are common sense reality, systems discussed, represented by classical physics, and then systems discussed, represented by quantum physics. And a system for us is just a collection of elements in interaction. And physics models require measurements and mathematics, where models of common sense reality resist mathematics in a certain way. We will see that in a minute. And then systems like models, are created by human beings in the sense that human beings demarcate certain levels of granularity for their elements and certain types of interaction between those elements, and so on. So once we've demarcated a system, then it survives of itself, as it were. So we don't demarcate its behavior, we demarcate the kind of behavior, the kind of element that you start with, but the system may then evolve in all kinds of horrible ways. As for instance, the Chernobyl nuclear power station started off as what we call a logic system, but then for one reason and another, it became a complex system which we could not control. And we call simple systems logic systems in order to avoid a confusion between complex systems on the one hand, which are a thermodynamic understanding of complexity, and complicated systems like the Chernobyl power system before the catastrophe, that is a very complicated system, but it's still a simple system because we can predict its behavior within the parameters which assume that all the people working in it do the right thing. So we call simple systems logic systems in order to emphasize the distinction between the logic system versus complex system on the one hand, and the more common simple system versus complicated system on the other hand. There are something like 100,000 papers on AI which have been let me see if I can, which have been published on arXiv since the release of ChatGPT. And I don't know, a huge fraction of those papers are about what they call complex systems, but they don't understand the thermodynamics meaning of complex system. And so what they almost always mean is just complicated systems. All right. Now, common sense is something that we're all experts in. I don't really need to say anything about it, but it is a demarcated realm of reality, which is demarcated to include mesoscopic entities, both objects and processes. And if you're interested, there is a very nice clarification of what common sense is. It's a collection of theories which are shared by all cultures. And he calls them primary theories. So they're theories about how to cook food, how to avoid freezing, how to build a house, and so on, which are shared by all cultures. And then there are secondary theories such as quantum physics or four-dimensionalism, which are shared only by a subset of cultures. And so common sense is by definition universal, leaving aside freak features like the theories of snowballs said to be rampant in Eskimo cultures. All right, so you can't apply mathematics to common sense reality in any simple sense. So there is no perfect circle, and so there is no mathematical circle in the common sense world. When we demarcate entities in the common sense world, we can count them. And so very simple arithmetic can be applied to the common sense world, but we can't apply the differential calculus or Euclidean geometry to the common sense world. And it's only when we start doing physics that we need measurement and mathematics. Now, BFO was not built deliberately to be an ontology of the common sense world, but for the purposes of this talk, we can think of it as the ontology of the common sense world. And it perhaps contains some things which don't play a role in primary theory, but everything in primary theory, I think, fits into the BFO framework. But that's neither here nor there. As you will see, we don't really need to say very much about the structure of the common sense world, other than the negative features that it doesn't involve mathematics and measurement. All right, now here we're dealing with system elements such as rabbits and tennis balls and buildings and people and even planets, perhaps. But when we move to classical physics, then we're dealing with the same sorts of things. Certainly we're dealing with planets then. But when we move to quantum physics, we move outside the level of granularity, the mesoscopic level, which is characteristic of BFO, and we move to the very low level of fine-grained entities. And similarly, although I won't be talking about general relativity theory, when we move to very high speeds and very large entities, then we again move out of the realm of common sense. Now, when we're doing classical physics, then we are picking out systems, they're fiat systems. We're picking them out because we can carry out measurements to those systems. And then using mathematics, we can make predictions about the behaviors of natural systems. And that's how classical physics evolved. So we have now a very good theory about causes and effects. It's called Newtonian mechanics, which works very well for the purposes of common sense and which works very well for the purposes of engineering, because we can make predictive models of these subsystems, which we create, for instance, when we create new kinds of industrial processing. And the possibility is that we create special experimental setups, for instance, a vacuum cylinder where we try and measure the speed at which a feather and a stone will fall, and we discover new laws. So in physics, we can discover new laws, and we often do this by building special experimental setups which are in the common sense world and which are subject to the laws of classical physics, as far as classical physics is concerned anyway. Now, mathematics ontology is not a big deal. I have been requested over the years over and over again to build a BFO-based mathematics ontology. And I've told people we don't need a new mathematics ontology. We already have one, and it's roughly Cantor's paradise. So it's roughly the ontology of set theory in all its miraculous extensions. And so this is our basic picture of the groupings within Matho. There will be mathematical entities in the proper sense, which include constructors, monads, and essential structures such as equations. And then there will be the structures themselves will be applied, for instance, to monads applied to monads in order to create more complicated essential structures, which represent then more complicated set theoretic entities, and so on, without apparent end. And it would not make sense to create a new ontology along these lines, but we believe that it's important to understand the nature of mathematical ontology and of mathematical entities in order to understand physics. All right, now the physics ontology, which I'm going to present, I'm not going to present it in detail either, that there has been no real demand for a physics ontology. And what I'm going to present here is not the physics ontology in the whole, rather it's just a simplified diagram of possible beginnings, a bit like the Matho diagram from a minute ago. But it relates to entities which denote universals, which have separable instance in reality in the same way that we have universals and separable instances in the chemistry and biology and the industrial ontologies that we've been building and which have been very successful. There is no counterpart of these ontologies in the physical domain. But given what I say here, namely that in order to build an ontology of a material domain, we need general terms denoting universals, there is going to be a problem for quantum physics. I mean, there's a problem also because of separability. The problem is that we don't really have universals in quantum physics that we understand. So we don't really know what a photon is, either as a universal or as an instance. And so it's going to be very hard even to start building an ontology of quantum physics. All right, so this is Physo. And I'll just talk about system elements, which we've seen already. So a system element may be a weight on a pendulum. The pendulum itself is a system, or the weight on a spring is another system, which is illustrated here. The bottom line is just examples. They're not part of the ontology yet. And then we have magnitudes, and then we have models. So the models may be mathematical models, graphic models, and so forth. So this is no big deal. And now we're going to draw a distinction between classical physics and modern physics. And by modern physics, we mean here just quantum physics. As I say, we're not going to deal with general relativity. So that everything here that is white is physics ontology, and the shaded part is mathematics ontology. And so we're saying that the system elements in classical physics are roughly equivalent to the objects in BFO, so that they're the same. And nothing hangs on that. But it's not interesting to challenge it because there are much more controversial things coming down the road in a few minutes. But modern physics, which means quantum physics, is such that there is absolutely no overlap between BFO and the physics ontology. The physics ontology for quantum physics, if one could build it. Moreover, here we find an essential role for mathematics, but the essential role for mathematics goes beyond the realm of system elements. Now I don't understand, you don't understand anything of what follows because nobody understands quantum mechanics. So we don't know what that means, as we will become clear in a minute. So let's think about photons. So photons are outside the realm of common sense. And if it's true that common sense is somehow a cultural universal, somehow genetic, then it's reasonable to suppose that what is outside common sense will not be understandable by people like us. So we have laser beams, which are system elements. They're part of common sense reality. We can see them. They're made of photons, but we don't have one photon as a system element. Rather, when we talk of one photon, we're referring to a probability density, which is an excitation in the electromagnetic field. And system elements in electromagnetic fields cannot be understood. We can only illustrate them mathematically. So we can do mathematics in order to understand something about system elements in quantum field theory. But these involve extending the realm of system elements in the quantum physics ontology, such as it is, by going beyond system elements to include other entities, which we will meet in a minute. All right, so there are two kinds of physics. There are physics which use models that we understand, and then there are physics which use models which we do not understand, except in virtue of the role of mathematics in formulating, for instance, predictions, which experiments in quantum physics notoriously and very impressively allow. So under one, we have deterministic models, which allow mathematical predictions, which allow engineering, including engineering of devices which involve quantum phenomena. The Large Hadron Collider, for instance, was built using classical physics, and we understand what we're doing when we build it. We just don't understand what happens when it does its work as a particle accelerator. And so then we have models, many very interesting models of quantum effects of various sorts. And so what is to come next? So many people, including David Chalmers, thinks that we can already see on the horizon a universally valid theory of quantum physics. The prediction of the Higgs boson is an example of a really impressive quantum prediction. It was statistical in nature, however. It was not deterministic, and it's thus not useful for engineering purposes. We can't build new kinds of devices in virtue of the fact that we can, in some sense, measure the existence of a Higgs boson. Now, there are some people who believe in quantum computers, but, and this is something else that Jobst and I, primarily Jobst, who actually knows this field much better than I do, talk of quantum computers is still mostly hype. When people talk of quantum computers, they often mean something else, not a computer, but something like an annealer. All right. So now we have the complete picture as far as it goes. So we have system elements, which we discussed. Then we have magnitudes. Now, in the realm of magnitudes, the physics ontology, extends beyond the realm of system elements. So there are magnitudes both inside the domain of system elements and also outside the domain of system elements. And things like frequency would be very simple examples of classical physics, which don't correspond to any system element in the real world. In the modern physics column, the system elements are themselves not in the real world anyway, but they are extended mathematically when we move to the level of magnitudes and models by abstract entities which do not have any system element role. So if we think of particles as being system elements in the quantum domain, which is a controversial statement already, then there are quasi-particles and virtual particles and similar hypothetical entities which we need to include in our ontology to make the mathematics work, but which don't really exist. All right. So everything with an X here is a creature of mathematical abstraction. Now, classical physics and quantum physics crisscross each other. As I've already said, the experimental setups in measurement of quantum phenomena belong to classical physics. They have to, otherwise we couldn't build them. And now we can use measurement data created or gained in quantum setups to make predictions. And we know that the predictions are validated, fantastically precise predictions. But we do not know what the data are about on the basis of which the predictions were made. Now, this doesn't mean that the matter in the quantum realm, if that is a reasonable phrase to use, is made of mathematics, which some people believe. We just can't say what matter is made of at the quantum level. We can say that a table is made of wood. We can't say things like that on the quantum level. And even if we could say them, we wouldn't understand them. All right, now, particles and quantum fields. Are quantum fields a mathematical construct which is used as a theoretical tool, or are they a fundamental aspect of reality? The answer, which we cannot understand, is that they are both. Now, there's a very interesting scenario here, which is defended, I think, by very few people, but primarily by this man, 't Hooft, who thinks that we're not yet down at the level where we will be able to understand quantum phenomena. We need to go deeper, and there we will discover deterministic laws. But to expose these laws, we need what he thinks of as real high energy physics. So the Large Hadron Collider for him is still low energy, it's boring. What we would need is a collider which is, I don't know, 4 planets large or something like that, so that we can get up to the really high energy that we would need to identify what are the fundamental aspects of reality. But we'll leave that aside. Most people do leave that aside. All right, now another part of the story is that it's not just quantum mechanics that we have to deal with. We need to deal also with quantum electrodynamics and with the other quantum disciplines. And each of these have subdisciplines and subsectarian movements within them, which are developing new experimental setups to treat new kinds of phenomena, and along the way creating new kinds of particles. For instance, electron holes are quasi-particles, but they move around, but they're not really there. And we can then add new properties to some of these quasi-particles to add power to our mathematics by saying, for instance, that the whole can have a positive charge, which is another sentence which we do not understand. And thereby, this leads to a spiraling of ever new models. So quantum physics isn't one thing, it's spiraling out in all directions. For instance, spiraling theories about what particles are, and that's what the Falkenberg book is all about. So in classical physics, as we all know, particles are discrete, independent, they're separable, they form point masses, they are parts of the bigger entities that we encounter in the common sense world, including all the experimental setups of quantum physics. And these are all very commonsensical kinds of views about what particles should be. But when we look at quantum mechanics already, the properties of particles overlap with the classical physics properties only 4 times out of 10, which is already, the other times we don't really understand. And if we move to quantum electrodynamics, then they overlap, I think, only 2 times out of 10 completely. And if we move to field quanta theories, so quantum field theory says that all particles are field quanta, then there are no particles anymore. There is heuristic mathematics that we can perform, but there are no particles. And then we have group theoretical views of particles, which provide a common structure for all the particles that I just distinguished, but then also at the price of there being any particles actually existing. And so this is, I believe, clear. So you need these virtual particles and you need the quasi-particles in order to make the equations work. So you have spirals on the side of new experimental setups. You have spirals on the side of new kinds of mathematics, which you need to make to work in order to make predictions. And then you have spirals on the side of new kinds of measurements, spirals on the kind of new kinds of visions as to what quantum field phenomena or quantum particles might be. And this means that we are not creating any kind of roadmap towards a unified theory. So this is a picture of the evolution of scientific large language models, I think over the last 2 years. And so there's a spiraling here because
Here are some images of evolution of scientific large language models, I think over the last 2 years from the web. Take a look.
So that was my phone speaking, creating another spiral. So I stole this from the web and my phone knew about it. I hope it doesn't do that again. So this is the kind of thing that we have in quantum physics. And it's ugly. All right, so we have setups, spirals, mathematics spirals, modeling spirals, spiraling out in different directions and at different speeds. So as we simplify and fine-tune each experimental setup to give mathematical results that we can mathematically formalize, then we get a spiral which continues. And we try to validate the laws associated with that spiral, but sometimes the validation fails and then the spiral is closed off. But as long as the validation succeeds, then the spiral continues to exist. Now, what is scope for mathematics here? So remember that Chalmers wants to engineer a simulation of reality, a perfect simulation. And engineering requires predictive mathematics. Now, we can have predictive mathematics in the quantum domain from Schrödinger's equation, but that only works where we're working in the phase space of the two smallest atoms, namely hydrogen and helium. All the other properties of atoms and molecules we can only assess approximately. And then we have to use combinations of quantum mechanics, thermodynamics, and classical Newtonian mechanics. Predictive models are almost impossible. All right, so as I say, Chalmers wants to engineer a simulation of reality, and this would include simulations of ourselves. But we can engineer both hardware and software only where we have predictive mathematical models. In order to simulate reality, we're going to need more than just hydrogen and helium. We'll need biochemistry, as well as neuroscience and all those other interesting disciplines. And they don't have, well, they have hardly any mathematics. Biochemistry is not a mathematical discipline. And the molecules that you need in biochemistry are, in any case, much too big for there to be quantum effects that we can discern. So there will be no solving of physics and no perfect simulation. And that is the end.
Thank you very much, Barry. This is very thought-provoking, and we have some of our prior speakers here. So again, we've had this tradition now of asking some of our track one speakers.
And can you let Jobst have a word also?
Absolutely. I see that. I see him. And I also see John Soa is here. And so I don't think Giancarlo is here, but perhaps we can start with our prior track one speakers.
I suspect many people didn't understand what I was talking about.
Well, we have some comments and comments and questions in the chat. But I thought that Michael Gruninger, for example, would have some comments on this.
I can take it, Michael.
I could also answer questions if needed.
I also have a question.
Yes, go ahead, Nicola.
Yeah, I wonder whether it would be possible in future to understand models that we now do not understand. I mean, it is this impossibility of understanding. Is it intrinsic in reality, or maybe in the future, sooner or later, maybe we shall even understand the quantum physics?
So, as you know, Nicola, I like brave hypotheses. I don't like to compromise. I think that the fundamental wave-particle duality, which is everywhere in quantum physics, is essentially not understandable by organisms like ourselves.
So in your opinion, the work done, there are many philosophers who are trying to work on the ontology of quantum physics. One of those is Claudio Calosi, and this is one I know. But so their work is useless because they are trying to capture some ontology behind quantum physics.
I think Jobs should answer that
Yes.
question.
So nice to meet you. Good evening. I mean, it's evening here in Europe. So basically, what we think is that what we know is that all the equations we have in quantum mechanics, all quantum field theory, all the different varieties around the quantum world that we have, quantum electrodynamics, everything, that these equations were set up to model what experimental measurements we have. That's what Schrödinger did. There is no way to explain the Schrödinger equation. The Schrödinger equation just describes the probability of a particle given some intention of measurement, like location, momentum, angular momentum, and so on. And so, but we don't, all these equations are just mathematical entities, or actually mathematical Wesenszusammenhänge, so complicated mathematical entities, which are connected to the measurements, and which can also allow us to predict measurements in quantum physics stochastically. And if you do enough measurements, you get exact predictions over the ensemble of measurements. However, we have no idea what the mathematics is modeling. And so if you do, and that's why our view is that quantum physics is ontologically void. Ontologically void means that we have only idealities from mathematics that describe the experiments and let us also plan new experiments, build us devices like lasers, like the NMR and many other quantum devices, or Josephson junctions, and you name it. However, they are ontologically void. So the attempt to create an ontology of them in the way that we can create an ontology of the mesoscopic world is fruitless. And this is very, very plausible. And so if you try to, for example, give an ontological meaning to the second derivative in the Schrödinger equation, you are basically trying to attribute an ontological meaning to a mathematical entity, which you can do, but then you end up with an ontology of mathematics. And that's why in the diagram that Barry showed on the right-hand side, where you have the models of physics, all of them, also those for classical physics, are made of idealities and or essences, as you could say. And so when you distinguish, that's what you have to keep in mind. So you can create an ontology, but you should not make the mistake to try to use ontological entities from the common sense world for this. But you have to bear in mind that these are like the number pi, like the perfect circle, and many other all mathematical entities. These are merely idealities. And this is, I think, the basic distinction that needs to be made. Because if you don't, you make a lot of philosophical mistakes. You basically commit a fundamental categorical mistake, which happens also when people start saying, oh, talking of space-time as an ontological entity. Space-time is purely mathematical. And this has to be borne in mind. Then one can work with this, but knowing the limitations. And to the first question, because these entities are purely mathematical, we can only understand them mathematically and not materially. Nevertheless, this is great, and it's great that we can do this, but I don't think it's possible to us to reach a material understanding. We just can't imagine what spin is, what angular momentum is for a quantum entity. We can only write a mathematical equation, and all the textbooks of physics do that, and none of the reasonable ones understands everything, but many contain ontological mistake. Like they say, for example, they say angular momentum, quantum angular momentum is quantized because the solutions of the Schrödinger equations only let us allow solutions with natural numbers. And because natural numbers are, of course, quantized and not continuous, then they say because of the equation, angular momentum is quantized. That's an ontological mistake. To get it ontologically right, you have to say there is something in nature which we measure. We don't know what it is, but when we make an equation of it, the solution to the equations are quantized. But of course, the nature of the equation cannot allow us to causally say that because of the equation, these phenomena are quantized. So this is just a short, bit deeper view of this.
I have another question, if I may, to Barry. You said that that Buffo basically covers classical physics. Still, it seems there are some notions of classical physics which are still complicated to handle from the ontological point of view. For instance, I wonder what a force is in Buffo.
Yes, so that's a very good question.
Acceleration, all these things. As
we are actually, and have been for some time, working on an extension of BFO to deal precisely with things like force and acceleration. That will be the basis of the classical physics ontology. And so we have a lot of ideas. We don't yet have the kind of consensus among all the people involved that we would like to have.
What's very important, Nicola, is that if you think of physics ontology, consists of system elements and systems, and in the middle you have magnitudes, and on the right-hand side you have the mathematical models. Also for classical physics, the mathematical models cannot be part of BFO, because BFO cannot model idealities. And so you have to see that we need to live with the fact that a part of the reality described by classical physics is also not part of BFO. And for the magnitudes, they are with regard to classical physics, part of BFO. However, this is a very important point. For example, the notion of force. If you read a textbook of physics, there are only circumscriptions of what force is, right? But there is no, what is the true nature of force? Physicists don't know. And because of this, we also cannot, in the ontology, say force is the following and be cleverer than the physicists. So essentially, we have to say we can also only work ontologically with the solutions that physics has come up with. And this is very interesting because at the deepest level, we don't know what constitutes gravitation, which is an important force, or, for example, the Coulomb energy, right? The potential energy of an electron. We can have an equation for it, but we don't really know where it comes from. And because of this, the ontology is also limited. And that's also true because the Coulomb force is, for example, a force of classical physics. So even in classical physics, we get very quickly to this problematic sphere that you described. So that's a very good point. And I think due to the nature of physics, we have to live with that.
Let's turn to Michael Gruninger. He's had his hand up for a while, and if John Sowa can unmute himself as you have a comment or question, that would be good, and then we can go to Ravi.
Thanks, Gary. I have two questions. One is, I guess, an objection over to Job's stronger positions. I think Jobs is making stronger claims than Barry was. In fact, I would disagree, particularly with that last statement, which is ontologies have nothing to do with force because the physicists don't know what it is. I think it's our job as the ontology community to help figure out what force is from that common sense perspective. I mean, the idea being that our ontologies are providing that conceptualization of how we understand the physical world around us. Force is part of that. Physics is one way of doing calculations and making predictions regarding force, but it's our job to be able to ground the mathematical equations of physics and other sciences within the conceptualizations of the worlds that we have as encapsulated within the ontology. So I would kind of make that point.
Let's say I agree with you. Would you then extend your rather generous approach to quantum phenomena?
I would as well, yeah. And I think because again, like quantum mechanics makes predictions. Those predictions are what we use when we're interacting with the physical world. Now, of course, those predictions may be, kind of counterintuitive from a perspective of, well, that's not the way it works when I'm sitting at my desk, but it certainly works when I'm, using a laser. I mean, I use a laser to read a CD, etc., or DVD. I expect things to work that way, and you need to have the quantum mechanics to be able to predict that. And I think an interesting point that Nicola made last week was, this the pop physics thing about talking about different interpretations of quantum mechanics, and I think that's kind of a different direction. And to me, the interpretation of the quantum mechanics is addressing a different point. They're not necessarily addressing a point of how do I kind of use the physics equations to make predictions about the world. They're more trying to come up with explanations, I think maybe along the line of Giancarlo's presentation, right? So you can also have ontologies that are providing explanatory power, but I think that's kind of a distinctive one approach than saying I want to use the ontology to kind of map the conceptualization of the world and the mathematics of physics.
But the core point we're making, Michael, is that for quantum physics or modern physics, the thing that you want to do, which is basically correspondence between the natural world in which we live and the mathematical world that describes the quantum phenomena, there is no correspondence. And this is now total consensus, right? I mean, if you read Falkenberg's book, she shows, and it's now more or less consensus among in a theory of science that the correspondence principle breaks down in particle physics. And so we cannot do this correspondence exercise for modern physics. For classical physics, we can, of course, to some extent. But for example, to take your force example, we can, of course, if you take a dictionary of philosophy, there are many, many views of force. You can ontologically describe them, right? And put them into a nice ontology, but that's not the force of physics. And so if you talk about the force definition of physics and want to ontologically map this, then you always magnitudes and mathematics, and then you have ideal entities. That's the point. So we just have to be honest to ourselves that when we want to make an ontology about the world in which we live, that's a different exercise than making an ontology about physics, because there we are absolutely, even in classical physics, totally bound to using mathematics. Also mathematical entities, so even in classical physics, you have the manifold, which is central to Hamiltonian physics, right? So this is classical mechanics. For many particle systems, you have Hamiltonians, so you have manifolds, and you have symplectic geometry. Symplectic geometry is extremely complicated mathematics. It's harder than quantum physics mathematically. It's unimaginable. These are pure abstract entities, but you need them for classical physics. So this is very important to see that there are limitations to what we can model, and if we want to be honest, we should separate these spheres and deal with them in the way that Barry described it, I think.
Okay, my second question was just, to what extent do you guys feel that you are the heirs of Hilbert's sixth problem? That this work is what Hilbert was looking for?
I think that it may be said that we are more pessimistic than Hilbert. So just as we're pessimistic in the AI book about the possibilities of artificial general intelligence, so we're pessimistic about the possibility of a universally agreed upon theory of physics.
Okay, you're disinheriting yourself. Okay.
That's fine. That's fine.
Yeah.
we have plenty of other good ideas in Hilbert.
Okay, thanks.
I see that John Sower is unmuted. John, do you have a comment or question?
Well, yeah, one of the things that we have been doing at our company, and now it's Permion Incorporated. Formerly, it used to be VivoMind, and then in the olden days, we had a general framework for building ontologies, but we did the construction of our ontologies dynamically by reading textbooks and ordinary language and analyzing the language and creating an ontology specifically for the subject matter that we were discussing, and we could dynamically add more and extend our ontology as we needed to understand whatever problem was under what we were discussing. Now, with our new Permion system, where we have changed the fundamental underpinnings in order to support the LLMs, the large language models. And what we're doing now is incorporating a way of understanding, of doing a formal representation of what's being processed with these LLMs. The LLMs are very, very flaky, and basically what they do is abduction. They make educated guesses about any subject matter, but from those guesses, all bets are off. You don't know whether it was correct or not. But we combine the abduction, deduction, and induction in order to pin it down so that we can have a very precise formal ontology for any subject, whatever that is under discussion. So we don't really have a finished top-level ontology. We have a very general framework which we can extend and dynamically adapt to whatever subject matter is being discussed. And we actually read the text books that we are studying and map them into our ontology and construct an ontology from whatever the subject matter happens to be. Now, I find that much more convenient for an open-ended variety of subjects.
So I have the suspicion that you're making your life too easy. But I don't think what you're doing bears on what we are trying to do with BFO, or what we're trying to do when we're seeking to extend BFO to deal with some of the phenomena of physics. We'll have to see the fruit that is in the pudding. We'll have to see which approach gains the most traction over time.
Well, we've had quite a bit of success, and one of the things that we had a requirement to do Chinese. Now, we've had basically a couple of different languages supported by our system, and there was a request from a client that required Chinese. And so there was an unemployed Chinese linguist. She had been teaching, but then when she had a couple of children, she wasn't able to continue that. And so what she was doing, she was very happy to get an assignment where she could work at home and develop an ontology and develop a
So, John,
Chinese.
this is all very impressive, but I don't think it bears on what I've been talking about.
Well, the thing is, the point that I'm making is that it's very important to be able to create ontologies dynamically that can apply to anything. They can apply to Chinese or English.
Yeah,
or
I agree. That is a virtue. If you can reach that state, then you have done something good. No argument there. But we're not trying to synthesize that particular virtue.
Okay. As usual, Ravi has some comments and questions, so we can turn to him. We also have another talk coming up next week, and so I thought Ken might say a few words about that before we leave. Looking at the chat, Greg Sharp, for example, has been very active on the Ontology forum and has something in the chat that he might be able to talk about. And then if there's time, we can get to Mike and Alakan, who's also on the chat and has some questions. So with that, let's turn it to Ravi.
Yes, thank you, Gary. First, I want to thank Barry. I thought before coming into this, I thought, oh my God, physics and ontology. I think you tied three things well: mathematics, classical physics, models, and ontologies, especially your work. Great progress. Now, you referred three people, Professor Landgrave, who is here with us, Chalmers, and Wigner. I spent more than a decade with Wigner because his partner was Bright, Gregory Bright, who, by the way, spent his last few years at your place, Buffalo. So Wigner is the first example of how mathematics is to be used in physics. Lately, there were earlier, whom Ken can talk a lot about, who brought the concepts of Lie groups, and so on. but group theory and quantum mechanics were the first breakthrough by Wigner in a big way. So that is very good. Now, why we don't understand quantum field theory as far as ontologies are concerned is the same kind of thing that John tried to slightly address, but not from physics point of view. See, when you don't have models, you're trying to create them from probabilities and AI usage, then you get into probabilistic discoveries. I first wrote in my chat, you will not have predictive things in standard model, but you correctly contradicted, and I agree with you, that Higgs was a prediction, but it was a statistical prediction rather than analytical prediction of the standard model. So wonderful. So going forward for getting the riddle of quantum ontologies, quantum-based ontologies, we need to understand multidimensional space. We need to understand how mathematics and physics are dynamic as the models develop. And then perhaps we'll have a role for ontologies. That's all I want to say right now. Later we can discuss one-on-one more. Thank you.
Good.
Okay. If there's no response from you or Barry or Jobst, we can turn to Ken to tell us a little bit about the next talk. Not that we're finished here, but I just wanted to make sure that as we get to the hour, people have an opportunity to know what's coming next. So Ken, can you say a few words?
Yes, next week I'm going to make an attempt to kind of summarize and synthesize what we covered so far in the summit. What we've covered so far is really pretty impressive. And summarizing it is not going to be easy. But I'll make an attempt to do so. And then make a few comments and move on to the next track where we will hopefully continue many of these discussions. John Sawa is planning, I guess we're now scheduling him for February 26th. So a week after, 2 weeks from today. And I'm still working on getting firm commitments from other individuals for the later talks in that track, but hopefully I'll have more to tell you about that next week. So it's
Okay. If I
that's
understand
basically
correctly,
what's coming up.
you wanted to say a few words in next week about mathematics and ontology. You have some views on those types of models, right?
Oh yeah, I will be talking about mathematics, about a number of things that I think relate to what we've discussed so far.
Do you have any direct responses to Barry and Jobst at this point?
I'll talk about that next week.
Okay.
Let's not get into a discussion now since we're already over.
Okay. If we can, Greg Sharp has been part of discussions on the Ontolog forum, and he raised the issue in chat about the ontological void. What ontologies do we have about voids? Boundary logic, he asked. So maybe he can address this, or
Yeah.
our speakers can.
It's not an area of expertise for me, but I have come across sort of void being a primitive for sort of ontological development. And I'm just curious if Barry had any thoughts about, coming from the other side. If void is the problem, what if you started with void, and how far could you get?
So one of the sources of BFO was work I did in the field of geographic information science. And one area of geographic information science is the distinction between a mountain on the one hand and a canyon on the other hand. So the mountain is made of matter, the canyon is not made of matter. And that led me to think about the ontology of wholes. And I have quite a number of early papers on the ontology of wholes. And the gist of those papers made itself felt in the way BFO was designed. So there are fiat object parts in BFO, and there are fiat boundaries in BFO, and there are sites in BFO. Now, the word site is another word for whole. So a site is the kind of thing that you can live in, so that the interior of your mouth is a site. And now the quantum mechanics idea, actually, I guess it's quantum physics idea of quasi-particles as holes where electrons can fit, that would fit quite neatly with the idea of site in BFO, but that they then go on to say that quasi-particles can have a positive charge, which just seems like it's destroying a good idea with a bad idea. But they do it, of course, to make their mathematics work, and that's the way they work. Everything is to make the mathematics work.
I mean, the way that the void is getting used in quantum mechanics or the vacuum, which is a fundamental principle of quantum field theory, is used to create a setting, as Nancy Cartwright describes, where then the mathematical models can be set to work. So in physics, we are abstracting from the reality we observe and reducing it until we can in the end fit the equations onto it. And because what is so great about physics is that though the models have to be created based on a reduced reality, they still are highly predictive, especially to build technical entities. And that's the beauty of it. But this should not lead us to misunderstand the reach of physics. And I think this is a very, very important insight by Cartwright and Falkenberg. And we've tried to also use this ontologically. In one aspect, which Barry didn't focus so much, but somehow by alluding to Chalmers, is that people who don't have this deep understanding of physics tend to overestimate physics and what it can do, and then base their ontology, but also their view of reality on this overreach of physics. And this is what we try to avoid. And I think this is a good practice to be modest with regard to what the human mind can achieve. And in the end, that's the philosophical foundation where this idea comes from. And it's interesting that Falkenberg, of course, takes this from Immanuel Kant, but Nancy Cartwright doesn't at all, which Barry would likes more, but it leads to the same conclusion of modesty with regard to the reach of physics. And whenever you look at physics, no matter which discipline, you always see it. And with thermodynamics, we have a discipline of physics which has mainly negative results, right? And everyone looks at electromagnetism and quantum physics for positive results. But basically, we also have to see that in thermodynamics, there's a huge theory that gives us a lot of negative results, telling us what we cannot know. And this has been in philosophy of science not appreciated enough. And in the ontology of physics, we are working on. We try to give this more room and to highlight the importance of the negative results of physics.
So Mike Bennett has his hand up and has a question on holes. So maybe he can chime in now.
Thanks. I'll be very brief and very timely. You just mentioned electron holes. So moving away from quantum, as a simple electronic engineer, two things you said that concern me. One was about electron holes, the other about frequency. I didn't quite catch. You said it wasn't real or wasn't a thing or something. Now, I want to be able to talk about hole conduction. I want to be able to talk about electron hole as something with a positive charge and so on. So I have a simple need to be able to deal with that conceptualization. And likewise, things like frequency, it's simply a reciprocal of time. It's a simple conceptualization. Are you basically saying that BFO is too ontologically pure for me to be able to use it in simple, common sense electronic engineering applications?
I hope not.
I would, can I answer this? I would say that you can, if you are aware that the perspective you're taking on, for example, a positively charged electron hole, that this is basically an engineering concept or idea that you can work with in engineering, then you can use it. You just have to see that it is not a classical universal, right? It's not a universal like a tree or like me as a person. There is a person, and I am an individual that is an instance of the universal person. You don't have this with quantum terminology. You have to be aware of this, right?
So Jobs, Alakan, Susan had a comment here that might relate to this. Did you mean that mathematical entities are not real?
Well,
you talked about them ideal.
There's a very big problem. Yes, so go ahead. So think of the number pi. The number pi is not mind independent, right? So pi is a mathematical idea that is used to define a circle, and that arises from thinking about the geometry of the circle, from trying to understand the circumference and or the surface of a circle. This gave rise to the number pi. But there is no number pi in reality. Without humans, there wouldn't be a number pi. So this is a mind-dependent entity, which we call an essence, or what's the other term we used? A very mathematical entity.
Essential structure.
Yes, essential structure. And you can't find pi in the real world. In the same way, you can't find a circle that is defined by the circle equation in the real world, because in the real world there is no set of points that has the exact same distance from one point, which is a mathematical definition of a circle. All the circles that we see in reality are if you zoom in on them, they have, of course, different distances of their delimiting points to the center. And because of this, the mathematical entities are mind-only entities. And this is a big problem also of analytical philosophy, because if you only allow empirical entities that are real in the world that we experience, you cannot. There's no room for mathematical entities. That is the point that we make in this paper that Barry showed.
Okay, our speakers are very generous with their time, but if we still have some time, Greg Herbert has a comment in the chat. It's about graph theory. You might take a look at that, or George might be able to unmute and tell us what his comment question is. John Soa, of course, has his hand up again. So if our speakers still have time, maybe we could get at least those two in.
George, John should try and formulate a question which has more to do with the talk, I think.
Yes, I agree. He may have. But can you read George's in the chat about graph theory permitting tracing paths that relates the cause to effect and talks about state change? I'm not sure if George. Yeah, George is unmuted.
I'm on board. Thanks for the opportunity to bring it up. I had some concerns in the beginning, and I want to be sure I understand that deterministic and non-deterministic distinction. It seems to me that we can still model non-deterministic systems using graph theory, network science, what have you, to provide useful results, useful observations of the tangible universe. I agree that in the quantum world, that's probably not feasible or even possible at this time based on what we know or don't know. But I don't think the distinction between determinism and non-determinism is necessarily a distinction between engineering and complex systems.
Oh, I agree totally with that. So I think what you say, first of all, graph theory is, of course, an algebraic theory from mathematics, a part of algebra, and it's a very useful mathematical model for deterministic but also non-deterministic processes. Think of Markov models that are also graph theoretical models that model non-deterministic processes. So that's all out of question, but all these are, of course, mathematical theories. Now, so for the big distinction that we are making, besides the distinction between mathematical entities and real entities in the sense of BFO, is the distinction between complex and non-complex systems. And I think this got mixed up a bit. So the second distinction is the following. A simple system is a system which can be adequately modeled and also comprehensively modeled with a mathematical set of mathematical equations. For example, the solar system as a gravitational system, or the hydrogen atom as a quantum system. So we have the Schrödinger equations for the hydrogen atom, which almost perfectly describes the hydrogen atom, and we have the same for the solar system with classical Newtonian mechanics. And if we make enough measurements on a hydrogen atom, like on the spectral lines, which are formed by millions of, if you put an electric current through a hydrogen gas, then you get spectral lines. And these are, of course, the result of many, many quantum events. And they then are deterministic, because the spectral lines of the hydrogen gas are always the same if you apply the same charge on the same volume of gas at the same temperature. So we are not, all of this is clear, but then there are all natural systems are complex systems where basically the laws of physics are only valid approximatively. And this is basically very, very important and a very important distinction. And this is what I mean when I say that we have underestimated the negative results from physics, because thermodynamics tells us that natural systems are always complex, and that it's very rare that we can approximate them adequately with mathematics. And so when we do this, we always have to withdraw elements of the system and simplify. However, when we build systems ourselves, then we can build simple systems that are perfectly obeying the laws of mathematics, like the laser. It's a quantum system, but because so many photons are emitted, we have then a stable macroscopic phenomenon. And so therefore the engineered systems, they are always, when they work, or at least in the way they work, are logic systems, but natural systems are complex. And there we very quickly come to the boundaries of mathematical modeling. That's the true distinction.
Before we turn to John, I'm just wondering, mathematics are not the only models we sometimes use to explain things. And there's things like analogy. So the idea of electronic spin is analogy to what we see in the meso world. So there's lots of, I'm just wondering if your comments on using metaphor and analogy to help us as one step closer to things.
Yeah, so the part of the talk which I didn't present because it was long enough already is a kind of taxonomy of different kinds of models. And you're right that there are, you can use models for all kinds of ways. You can make a model of the Shakespearean monarchy system, for instance, or you can make a model of the historically existing monarchy system in England or in Bavaria. And in fact, that's one of the things that we're trying to do. We're trying to extend the approach that we presented in Physo, the physics ontology, to create an ontology of historical systems, like capitalism or feudalism and so forth. And that we won't have any mathematics at all, except dates, maybe.
Okay, maybe John, do you have something relevant to ontologies,
Yes.
models, physics, and mathematics that we can hear?
And yes, and the point that I make is that that no finite ontology can ever be adequate for handling the real world and all of its interactions at every level, including quantum levels and everything else. Therefore, what we need is an infinite ontology. Now, of course, you cannot have finished infinite ontology, but what you need is an ontology system that can expand and add new branches automatically. And in one sense, I had been discussing these issues for many times about the psych ontology, and we had come to an agreement that pretty much what you need is the ability to expand your ontology forever with adding new components to it and new branches as you go along. And one thing that essentially the top level of an ontology is very underspecified, and it's really pretty much irrelevant. You can replace your top level ontology without really doing any damage to your lower level, because it's the lower levels that cover the infinite number of ranges, and that's basically the way the psych goes. And I had been discussing these issues. We have discussed issues about psych for many years, and the essential point that we came to agreement is that it's the lower level special purpose ontologies for special purposes that are most important. And you do need a framework at the top in order to organize them, but that framework must be infinitely expandable to handle absolutely anything. And so basically, the point is that no finite ontology can ever be adequate, and this is one reason why the LLMs are so important, that they are expanding and showing that you need an open-ended variety, and that's why we're developing an infinity of possible ontologies to handle I shouldn't say infinity of ontologies, but an infinity of possible branches so that you can expand your ontology in any direction as needed dynamically.
Sounds truly fantastic, John.
Okay, I'll talk about it 2 weeks from now.
Infinite work for ontologists. Let's turn to Ravi, and I would just ask our speakers, Jos and Barry, if you look at the chat, if there's anything you wanted to comment on, we can end there.
Okay.
So first, Ravi.
One thought. Appreciate what Mike Groninger and Mike Bennett have been saying. It's the engineering consequence of quantum effects that make an ontology possible. Application of physics in those areas which border chemistry, engineering, and proteins, etc. Now, what I want to say is there is another angle that you ontologists, all distinguished people, might want to consider. Quantum and information and AI are tied together. Okay, quantum computing, quantum entanglement, Rabi oscillations, Isadore Rabi. Remember Wigner and Bright's colleague? That oscillation, etc.
So this I would really like to
quantum information and topology are intimately connected with space.
But it has nothing to do with artificial intelligence. I mean, quantum computers are merely.
Yes, they do. They do.
So basically, I'd like to send you the chapter of our book of the new version about the limitations of quantum computers, and also there's a huge literature that shows that quantum computers can only do what Turing machines can do. Just in some problems they can.
No, it's beyond Turing.
Let me finish. They can do it faster.
It goes beyond Turing.
No, this is a myth that has been mathematically thoroughly rejected, and furthermore, it has now been shown that for the kinds of operations needed for machine learning tasks, it has been proven that there is no quantum acceleration possible, because the nature of quantum computer only allows acceleration for certain patterns, at least exponential acceleration, and so this is very important, and I would like to send you. It's a really big myth that quantum computers, if they are ever built, will change anything about AI. And we've really thoroughly rejected it, and we can certainly send you literature that our passage about this.
There are
Jobs, can you post a link on the Ontolog forum to that work so that the broader community can see it?
Yes.
Yeah, we could post. Barry, we can find a way to post this there. It's a good idea.
Okay.
Thank you, Professor Landgraf.
So, do either of you have any other comments on the chat that you want to respond to?
So there is a comment in the chat by Todd. Should BFO have an abstract term as Dolce does? And we are gradually exploring extending BFO in certain ways, better treatment of information artifacts, for instance. And some of that may look a bit like abstract entities. But you know that BFO advances very slowly because we have such a large number of users that we can't make big changes. So you will see in due course what we're doing. If Todd is still there, of course, maybe he's not there.
Okay, I don't see any more hands up. There's more in the chat, but if
Here,
our,
Barry.
yes, Todd?
But Barry, one of the reasons I brought that up, some of the discussion, unfortunately, I was delayed in joining, but some of what I heard certainly sounded like some of the mathematical entities that were discussed or needed would be considered abstract.
Yeah, but
in a
they're
more
not part of
general
BFO.
notion.
That's the point. Matho is a different ontology. And the connection between Matho and BFO is probably going to go through the information content of mathematics. Although there, Jobs and I have different approaches, but we will resolve our differences.
It's not needed.
Okay.
So Barry, Mike Bennett just posted something that maybe we should give you an opportunity to respond to about whether you've changed your opinion about what is real.
No, so very, very little has changed. What we're doing is we're finding, now let me get this right. We're finding features of reality, and force actually would be a good example in this connection, which we clearly need to be able to deal with. And in some cases, we can deal with inside BFO. In some cases, we have to extend BFO. And then in the case of mathematics, we need a new ontology. So we never sleep. We move very slowly in contrast to those people who build infinite ontologies.
One more comment to Mike. You said something in the chat about complex systems. So there's if you go into the theory of complex systems, you will see that it's consensus that complex systems have essential properties that avoid adequate mathematical modeling. One is, for example, the evolutionary character, that they add not only new system element, but new system element types, which mathematically correspond to new dimensions of vector space. Now, you cannot specify mathematical model in a vector space that changes while the mathematical model is being applied. That's just one tiny example of many. So in our book, you will find an entire chapter about this, about the properties of thermodynamical properties of complex systems that prevent mathematical modeling, or that make it, that allow it only to be adequate for subsystems or aspects of systems. Just as one more comment to your, there are many other clever things you said in the chat, but we cannot address all of them. But thank you.
Thanks. I'm intrigued because I always assumed that it was maths that taught us how complex dynamic system works. So your bold statement that they can be mathematically modeled puzzled me. I'll have to dig deeper and follow up what you said. Thank you.
You should read our book, Mike.
I should.
Version 2.
Well, it will come out in May.
Okay.
And it has a new chapter on physics and many new sections. But the basic standpoint is the same. In fact, we already, even though ChatGPT had not been released when we wrote the book, we have already in version 1 arguments to show why ChatGPT type artifacts must hallucinate. And the idea is that for any kind of AI model to work, it has to turn whatever is the source domain into a simple system, because computers can only execute programs which deal with simple systems. In our technical sense of simple.
And with that, I think we should end our session. I want to thank our speakers, Barry and Jobst, and everybody for coming. And I look forward to seeing all you back here again next week when Ken will be talking a little bit about mathematical models. Thanks, everybody.
Bye.
Thank you
very much.
Bye-bye.
Bye.
Bye-bye.
Thank you.
Bye.
Thank you, Barry and Professor Landgrave. Thank you, and others as well.
And thank you.